welcome back. First, let me make an announcement about a change of the program. So the first talk of this afternoon, draw Valentine will take place of Cam Gordon. So instead of Cam Gordon, Draw will give the first talk this afternoon. Yeah, and also let me remind also about the policy of questions. If you have questions, please first ask for the microphone before ask the question. Okay? And remote people, you can just unmute your microphone and then ask the question directly. So the second talk of this morning section, Helen Wong from Claremont McKenna College, and the title of the talk is Cover in Brackets, Skein Algebra of a Punctured Surface. Please.
Thank you. Thank you so much again for the invitation. It's a real big honor to be here in memory of Vaughan Jones. Before I start, I should say that I have trouble with time management, as my mother will tell you. And I tend to talk very fast, so please don't hesitate to stop me with questions, even if it means like finding the mic and just waving me down. I personally would appreciate that very much. Okay, so let me just start. So the story starts a little bit with the Vaughan Jones's discovery of the Jones polynomial. And this kind of really shook up low-dimensional topology, and then this was followed by Witten with his amplification of the Jones polynomial to three-dimensional manifolds. And from the topologist point of view, this really was like, you know, fell from the air, right? It came in and it showed that the right-handed trefoil and the left-handed trefoil were different in half a page, right? It proved Tate's conjectures, which were open for almost 100 years at that time. But so it really shook things up, but then there's this question that still remains, like, what does it measure, right? And I think Christian this morning tried to ask the same question, right? There's these classical things that we study, like fundamental group or homology or mapping class groups or volume if you're thinking more on the hyperbolic side. What does this, normal surfaces, what's going on? And so as a point of connection is this Kaufman bracket Skein algebra has emerged as this point of connection. It generalizes the Kaufman polynomial, and I'll show you a little bit from the definition. It's important in the topological quantum field theory, especially in the Skein version that Christian was talking about earlier. And it also, and this is the really important part, it relates to the geometry of the surface. And it's related to a deformation quantization of the Teichmüller space. I'll explain the story a little bit today. And so the Skein algebra is maybe the one of the few places where we can actually maybe connect classical geometric topology with this hyperbolic, with the quantum topology. So my plan for the talk is to define the Kaufman bracket Skein algebra and explain how it's related to hyperbolic geometry. And then that's for the standard Kaufman Skein algebra. And then I want to repeat that story for a punctured surface and a generalization of the Skein algebra due to Julien Roger and Tian Yang and Tan sitting there in the back. So I'm hoping he can help me if I have any questions I can't answer. And if time permits, I'd like to kind of go nitty-gritty into a little bit of the newer results. And this result about the Skein algebra with surfaces with punctures and how it's related to decorated Teichmüller space is joint work with Han von Moon, who's an algebraic geometer at Fordham University. Okay, so introduction to Kaufman bracket Skein algebra. So the story, of course, starts with the Jones polynomial. And as Christian explained this morning, earlier, you can compute it using the Kaufman bracket and the Skein relation. And so suppose you have a variable, q, and you can pick any invertible complex number. And you pick a square root of it, but that's for technical reasons. If you draw a picture of the diagram of the knot, you can evaluate it by resolving crossings, either one way or the other, and then you put some factor q to the 1/2 if you go one way and q to the -1/2 if you go the other way. And if you see a circle bounding a disk, you can replace it at the cost of introducing a -q -q -1 in front. And in all these pictures, I have, there's a framing, and I'm assuming its framing is perpendicular to the blackboard. Okay, so for every knot or link and a diagram, you can compute this Kaufman bracket. It turns out to be an invariant of the framed but unoriented link. Okay, so now if it's easy to see that if you pick a knot diagram in S3 and you do this process, you're going to get a Laurent polynomial at the end, right? And so if you look at all the, and if you look at now all the link diagrams, you notice that there's some calculations, right? So if you have two link diagrams and you put them next to each other, this is the same because of invariance into the Reidemeister moves as putting them over one on top of each other. And moreover, the Kaufman brackets multiply, so this gives you some kind of like multiplication that you can think of as happening. It's like multiplication of the Kaufman bracket corresponds to this putting next to or on top of operation in topological terms. Okay, so now you can generalize this by considering the structure of all the possible Kaufman brackets that you can get from all the possible framed links that you can draw in S3. And in this way, you can now think of, instead of just the Kaufman bracket for a single diagram, you look at all of them. So you take the module generated spanned by linear combinations, spanned by all the possible framed links, and then you mod out by the normal Skein relations. And this module in S3, you can also think of, comes with a natural multiplication of putting two diagrams next to each other or on top of each other. Either way, they're equivalent. And this turns the space of all possible Kaufman brackets in S3 into, gives it some kind of algebra structure. This isn't very interesting because these are just all the Laurent polynomials in Q to the 1/2. But you could generalize to arbitrary manifolds, which was, I think, done by Joseph Persitsky and Vladimir Turayev independently. So suppose you take a 3-manifold, and now we play the same game. We take all the possible links in that 3-manifold, we take linear combinations of them, and you mod out by these relations. But now, because you're in an arbitrary 3-manifold, there's no obvious sense of up or next to or on top of, and so you don't get this nice multiplication structure. All you get is that it's a module. So it's a priori not an algebra. However, there's a special case, which is the one that I'm interested in, where your module is a thickened surface, right? So I think about this as, you have your surface and you thicken enough, just enough so that you have room for crossings, right? And so you look at the same thing. You take all the possible framed links. So I think of these as links on a surface, but with over and under possibilities. And then you mod out by these relations. And now, because I'm thinking of a thickened surface, there's some notion of up, right? And you can multiply. So if I have two of these, I can stack them one on top of each other, and that'll give me a natural algebra structure. Okay, so just so that it totally makes sense. So over here is a framed link. I have a 1-punctured torus, and here's another framed link and a 1-punctured torus. If I multiply them together, I'm just putting one on top of the other. And once I have them one on top of the other, in the Skein algebra, I can resolve, for example, like this crossing here. And so I get q to the 1/2 times one resolution plus q to the minus 1/2 times the other resolution. And so I can keep on going, and this will give me something interesting. All right, so of note here is that because I'm on a thickened surface, over and under matter. Which one is over and which one is under? So over here, if I do this one, the second over the first, it's different than if I switch the order. And you can see this in these formulas because the different resolutions, I think, this is really hard to see. So over here, this resolution is a q to the 1/2, but over here is the q to the minus 1/2 because I've changed the over and under. And so multiplication in the Skein algebra is not commutative. And it has really interesting algebraic properties. So for example, the multiplication is not commutative except for some very small surfaces where things do over and under are the same. Or when you pick your variable so that the q to the 1/2 and q to the minus 1/2 are plus or minus 1, right? It's easy to see that if you have a loop around a puncture, you can make that loop really, really, really tiny, so then it doesn't matter, right? The order, you can swap the order with anyone else, and so it's central. But otherwise, Przyczki in 1991 showed that usually, except for the really simple cases, this Skein module, or the Skein algebra, is infinitely generated as a module, meaning there are many, many framed links with no crossings that are distinct on the surface, right? And so all of those will be generators. If you now put in an algebra structure, right, it's also finitely generated as an algebra, and there are certain presentations that are known, but for only a few. All right. More recently, we have more algebraic properties, and I'm not going to talk about these. It's just a list. The Skein algebra embeds into a quantum torus, and so you can show that it has no zero divisors. The center is generated by puncture loops when Q is not a root of unity, but if you are at a root of unity, you get some interesting ones related to Chebyshev's. There's a recent theorem, the Unicity Theorem, that if Q is a root of unity, then the Skein algebra is finitely generated finitely generated as a module over its center, which means that it's almost isomaya, and you can get all sorts of interesting algebraic properties about these. But the algebraic properties isn't what I'm interested in. What I'm interested in is this relation to this thing down here called the SL2C character variety. So somehow the Skein algebra is related to an SL2C character variety, which is also related to hyperbolic geometry. So that's the thing that I want to focus on next. So let's look at the hyperbolic geometry of the surface. Actually, before I do that, are there any questions? No, okay, all right. Okay, so now instead of thinking about the topological picture, I'm going to think about it in a geometric way, right? So suppose I have a surface, and it has a complete hyperbolic metric on it. So now I'm going to look at all the possible metrics, and this forms the Teichmüller space. And once you have a metric, you can talk about how long things are, right? There's a sense of length. And so if I have a curve in the geometric picture and a metric, then I have a well-defined length for that curve. Now, you can so you can create functions this way on the Teichmüller space. So define the trace function for a curve to assign. So for every metric, you're going to look at the length of that curve under that metric. And then you can create these trace functions, which for reasons that I'll explain, that'll become a little bit clearer. You take minus e to the length over 2 minus e to the minus length over 2. Okay, and so this is a function on Teichmüller space, right? So for every metric, you're going to assign this version of the length, right, with a little bit messed up. Okay, so now also, every metric corresponds to a monodromy. So instead of thinking about a hyperbolic metric in Teichmüller space, you could think of it instead as a homomorphism from the fundamental group to the isometries of the hyperbolic plane, which are the Mobius transformations PSL2R. Right? So one way I think about it is that if you take the universal cover for a surface, depending on what metric, the fundamental domain has a different shape, right? And so somehow this is this homomorphism tells you how to go from one fundamental domain to the other, right? So anyways, Teichmüller space is contained as a real subvariety inside the SL2C character variety. So here, for the monodromies go into PSL2R, now I'm in SL2C. And getting rid of the P is an easy decision, and then R to C is so that I can do algebra. Okay, so now I have this thing that is an algebraic variety, and it's well studied in the hyperbolic geometry world. Okay, all right, so now if I have this SL2C character variety, I also have, so now I have a homomorphism. Let me go back. Right. Ooh, how did I go back? Okay, so now the SL2C character variety consists of homomorphisms from the fundamental group to SL2C. right? Now, instead of thinking about curves, loops on a surface, I'm thinking about matrices. And for those 2 by 2 matrices, I can take a trace. So if I take the trace, right, so if I fix a K, and then I take the trace, right, put a minus sign in front, then somehow this corresponds exactly to the trace function that you get from looking at the lengths of that curve under the metric M. Okay. These trace functions generate the algebra of regular functions over the SL2C character variety, and here's the connection with Skein algebras. The trace functions themselves satisfy something that looks very much like the Skein relation when Q is equal to -1. So there's some sense of that what you could multiply trace relations and that it satisfies a Skein relation that looks like this. And this identity comes from some identity for 2 by 2 matrices of determinant 1. If you take trace of M, trace of N, you get trace of Mn, and then trace of Mn inverses. So that these correspond to, you can think of these as the 2 resolutions. Okay. All right, and the important thing here is that Q, these numbers in front are -1, right? And this kind of makes sense if you think about it, because we're now, up to now, looking at the fundamental group. The surface is not thick, so there's no sense of over and under. It's just a curve on a surface. And so in the fundamental group, over and under are exactly the same, right? And so that kind of makes sense here. And there's a theorem by very many various people. And I'm not going to list them all, but if Q equals 1, there's an isomorphism between the Skein algebra and the algebra of functions. And literally, it's just saying if you have a curve in the Skein algebra and you set K equals to 1 so that it's commutative, then you can identify in a one-to-one way with the trace functions on the SL2C character variety. And notice that both of these things are commutative, right, because we're on a surface. But in general, when we have the Skein algebra, Q is not equal to 1. It's not commutative. And so it's very tempting to say, to think that somehow the Skein algebra is some kind of non-commutative version of what's going on here. And yes, that is. This is due to Taurus. So suppose you take Q to be e to the 2 pi I h bar. Then the commutator relation spits out something like this, some number minus one of the resolutions minus some number times the other resolutions. But if you take the Taylor expansion by plugging in e to the 2 pi I h, you see that this thing in the front turns out to match exactly a Poisson bracket due to Weil, Pearson, Atiyah, Bott, Goldman. Okay, and so you can now, because of this Poisson structure, use algebraic geometry to kind of think of this SQ of sigma as a deformation quantization of the SL2C character variety. Essentially, when Q is 1, the Skein relation, you have plus or minus 1s, right? So let me go back. Okay. Okay, right here, right? When Q equals 1, over and under are the same, right? But when you now put a Q there, you're kind of making the Skein relation not commutative, and so that's kind of the general gist of it. Okay, anyways. Actually, this idea that the Skein algebra is this non-commutative deformation of the SL2C character variety, we know a lot more now. So there's a theorem that was just proved by Froman, Joanna, Kanya, Barthes, Joanna, and Tang Lei, and also by Ganev, Jordan, and Safronoff, that says that if Q is a primitive root of unity, and actually I think you can do this also when n is even or odd. There's some correspondence between the irreducible representations of the Skein algebra exactly with the character variety. And on a Zariski dense subset of the character variety, this correspondence is 1-to-1. Okay, this. Technically, I think we should say this smooth part, I should say Zariski dense, because the smooth may depend on whether, as I think Tong was pointing out last time I gave this talk, that it may depend on whether there's a puncture or not in the surface. Anyways, this correspondence going left to right and then right to left is very well understood. Okay, and so there's other things that you can do about it. I want to skip that in the interest of time. And what I want to do next so that was a little bit of a story about what happened with the Kaufman bracket Skein algebra versus the usual one. I want to generalize this. Okay, so what I'd like to consider is the Skein algebra surface with punctures, and to see if, and this instead of the Teichmüller space, to look instead at the decorated Teichmüller space. And of course, this was pioneered by Julien Roger and Tian Yang there. Okay, so suppose you have a compact surface with punctures. So now the decorated Teichmüller space consists of not just the metric, but a metric along with the decoration of a choice of horosphere at every one of those punctures. So literally, you just should think, okay, there's some shape of the surface, and then around every horosphere, you're going to pick, around every puncture, you're going to pick a loop, right? And you can pick it big or small, you choose. Okay, so for every point in the decorated Teichmüller space comes with a metric and a choice of these red loops. Now, the advantage of this is that now, as before, if I have a loop in the middle, right, then I have a well-defined length from just the metric. But because of these horosphere decorations, I can now also measure the lengths of curves that go from one puncture to the next. Okay, and just for fun, I'll also throw in the lengths of vertices by the length of the horoscope there. Okay, so here's the picture. So suppose I have an arc, right, that goes from one puncture to the x. Now I can just kind of lop off at where they meet the horosphere and measure the length in between. Okay, so I have a length of loops, length of arcs, and also length of punctures. And then you can define these lambda length functions. And they're called lambda lengths because, I think due to Penner probably, that if you have a loop, then you do e to the length over 2 plus e to the minus length over 2. If you have an arc, you kind of just take one of the terms, half of it, e to the length over 2. And then if you have the vertices, you just take the length of the horosphere as it is without any change. Penner proved that if you fix an ideal triangulation for the surface, so this is a triangulation where all the edges end at a vertex, at a puncture, then the lambda lengths of the edges parameterize the smooth functions on the decorated Teichmüller space. These lambda lengths satisfy not a Skein relation, but a Ptolemy relation. So if you do a diagonal exchange, then the length of E times the length of E prime is just length of A, length of C, times lambda, length of B, length of D. Technically, I should not say length, I should say lambda lengths. Okay. There's a Weil-Petersen Poisson bracket on the smooth functions on the decorated Teichmüller space. So these lambda lengths are smooth functions, and there's a Poisson bracket that was computed by Mondello. And based on this, Julien and Tan found relations between the lambda lengths, right? So not just the Ptolemy ones, but they found other ones. And they conjectured that the relations that they found were all the possible relations. Based on this, they kind of reverse engineered, looked at the story for the Skein algebra and tried to kind of copy what was going on there. And they defined a generalization of the Skein algebra for punctured surfaces. So let me give that to you now. So sigma with punctures, V1 through VP. I'm going to think of the V1 and VP as extra variables in there, and they're going to commute with everyone, right? And so I stuck them here as scalars, right? But you should think of them as generators, really. And then you look at all the framed links and the framed arcs, where the arcs go from puncture to puncture, and you have the two original Skein relations for crossings in the middle, but now you can also have crossings at the end, at the punctures. And what's interesting here is that if you have a crossing at the endpoint, you have, okay, so let's see. So for this one, you have a resolution that goes right and the resolution that goes left. Here, the same thing, you have a resolution that goes right and a resolution that goes left around the puncture. And what's interesting is that the scalars in front, right, the coefficients in front are now half of them. So now I have to take fourth roots instead of half roots. And not only that, but this relation also involves this VI here, right? So really, in terms of lambda lengths, you should think that if I have a crossing at a puncture, so two arcs end at the same puncture, somehow the length depends on the choice of horosphere that I made when I said chop it off here, right? So that kind of comes up in this relation here. And also, there's another relation for puncture, loops that go around the puncture. Okay, and multiplication is like before by superposition. So just to be clear, suppose I have this curve, then here I can resolve this one on the interior by the usual Skein relation. But then here in my picture, I also have Skein relation here, like crossing at the puncture, and I can also resolve those. But when I resolve those, I pick up a V down here at the bottom. Okay? All right. So Roger and Yang proved this theorem. So if Q equals 1, there's a well-defined Poisson homomorphism. So there's a Poisson structure that was computed by Mondello from the Skein algebra when Q equals 1 into the lambda length functions. And literally, it's just sending everyone to its lambda lengths. And if Q is not 1, then once you push it off, you can think of this as some kind of non-commutative deformation of the decorated Teichmuller space. Okay? And any questions? So this is really like a mimic of the story for the Skein algebra. And actually, so it almost says that that this generalization, this Roger-Yang Skein algebra, is a quantization of the decorated Teichmuller space. And in fact, I've given many talks where I did say this, and then Tian came up to me and said, not quite. So there's something missing in this picture that says that I can't quite say this yet, that it's a quantization. And what's missing is this injectivity of this lambda length map here that sends every curve to some version of its lambda length. Right? Another way of thinking about this is like I need to make sure that oh wait, I want to go back. I want to make sure that these relations that they found are all of the relations among the lambda that come from the lambda length functions, right? So that's kind of what the injectivity is trying to say. And so in joint work with Hanbom Moon, so actually, we proved that it was injective under extra conditions in 2019, and then now we just posted a paper on the archive where we proved it for all surfaces. And as soon as you have that this map is injective, then you can, based on earlier the work of Roger and Yang, you have that this Skein algebra is a deformation quantization of the decorated Teichmuller space. Okay, all right. So any questions before I move on? I also should check on time. So am I out of time or no? I have half an hour. Okay, perfect. Thank you. Like I said, I'm completely all right. Okay, so great. So maybe I can show you a little bit more. So our proof of injectivity actually relies on another algebra that is also based on the decorated Teichmuller space. So this other algebra looks only at the lambda lengths of arcs, and they ignore the lambda lengths of the knots and also the lambda lengths of the vertices. And this other algebra is called the cluster algebra, and it's the cluster algebra for surfaces that's due to Fomin, Shapiro, and Thurston. These cluster algebras are important in combinatorics and in Lie theory from Fomin and Zelewski for other reasons. And as part of our proof, we embed this cluster algebra into the Skein algebra, the Roger-Yang Skein algebra when A equals 1. And actually, we show that the two algebras have the same field of fractions. And so as a corollary, a side extra corollary, we have that the Roger-Yang Skein algebra is also a deformation of the cluster algebra, which is kind of, for the cluster algebra world, this is kind of interesting because if you take this, just the cluster algebra by itself, there's a version, you can make a quantum version of it due to Berenson and Zelewski. They have this machinery where you do that. But you need this cluster algebra to have this property called having full rank. And in the case of punctured surfaces, then it doesn't have full rank, and so they don't know how to quantize. And so what's really nice here is that this Roger-Yang, the Skein version, is able to quantize something that couldn't be done in the cluster algebra world. So All right, so I wasn't quite sure how, like I said, I'm really bad with time. So I wasn't quite sure how much time I have. So what I'd like to do, I have 2 sections left. One is to give a brief proof of the injection of the lambda length function due to Roger-Yang. But then that assumes that you know what I'm going to assume for a little bit that you know what a cluster algebra is, and then I'll go back and define what a cluster algebra is after that, if it's okay with you to do it in the kind of the reverse order. Okay, all right. So to prove, remember this, this map sends every knot, arc, and vertex to its lambda length, right? So now there's 4 steps to prove that it's injective. The first step is that if I fix an ideal triangulation and I look at all the multi-edges, so I allow not just edges, but multi-edges, and I say you're allowed to invert them, then this gives you an injection into the C infinity functions of the decorated Teichmuller space. Okay, so actually this step 1, I think, is already in the work of Roger and Yang. I don't think they use this language, but certainly this comes from a lemma in their paper. Okay, so now the second step is just algebraic geometry, or just algebra. If it turns out that this Roger-Yang has no 0 divisors, in particular, I'm allowed these edges in this ideal triangulation are not 0 divisors, then I can divide, and it still gives me an injection. Okay? So now if I put these 2 together, I now, in order to prove injectivity, really I only need to show that there's no 0 divisors in this Skein algebra, right? If there's no, and this is what I mean about there being no divisors, it's the Skein, the relations that you get from this, the 4 relations from the Skein algebra are all of them, is kind of what I'm thinking. And so we showed this in earlier work in the case where the surface has an ideal triangulation without self-folded triangles, and we did it purely by like combinatorics. You look at the curves, multiply them, show that it's always non-zero, right? And because the combinatorics is really complicated, we needed to assume that there were no self-folded triangles, but then in the general case, this was just a nightmare. So obviously we needed a new idea. And so the new idea came from looking at this cluster algebra. And so this cluster algebra is well studied. It's related, again, to the Penner's decorated Teichmuller space. It's generated by only the lambda lengths of arcs of ideal triangulations. And by definition, it has no 0 divisors. It's like within like the very first line of the definition, you see immediately it has no 0 divisors. And we show that there's an algebra injection, right? So I can inject it into the Skein algebra, which makes sense, right? Because in the cluster algebra, you only have lambda lengths of edges. In the Skein algebra, you have knots, arcs, and vertices, right? So there's more stuff there. And they come from exactly the same things. So, and then now at this point, it's just a matter of algebra, which Hanbaum is responsible for, to say that, okay, I have an injection here. This cluster algebra is naturally in the fraction algebra of some EIs. Those EIs are the lambda lengths of arcs in an ideal edges in an ideal triangulation. And so what you do is, okay, cluster algebra has no Skein, has no 0 divisors, so you make it bigger until it matches the Skein algebra. And so by looking at the Kroll dimension, you can see that if it stops, and these dimensions are the same, and you can do this process while keeping this extension of the cluster algebra an integral domain. And as soon as they match up, you can see that because this is onto that the Skein algebra also has no 0 divisors. So basically, it's just, the cluster algebra lives inside the Skein algebra. I extend this one so that there's no extra 0 divisors, and so everything matches up, and then I'm done. Okay. I should note that Wade Bloomquist, Caro, and Tong Lei all have an independent proof of integrality for this Roger-Yang Skein algebra. Okay, so, all right. So again, once I have that this is injective, you get that it's a deformation quantization, and also it's because of the proof we also get that it's a deformation quantization of the cluster algebra. Okay, so now that's the kind of the end of my quantum topology part. For the remaining, I don't know how many minutes I have, I'm going to do a quick course in cluster algebra just so that you know what it is and how to define it, so that it's not like I'm kind of lying to you about the existence of this cluster algebra and its properties. Okay, so I'm really sorry. This is really going to be a little bit fast, but hopefully not too fast. Okay, so a cluster algebra is a commutative algebra, and it's generated by all the, so there's this procedure. So what you do is you pick something called a seed, and it consists of some finite number of variables, x1 through xm. And so the m things, right, the x1 through xm is the seed, and for every one in the seed, there's some procedure to create another seed. Okay, so this is called mutation. So you have the initial seed, and then you have many mutations, one for every variable inside this seed. And there's some crazy formula that tells you how to create the new seed. Okay, so if you mutate it on the kth variable, then you get a new seed, and there's some relation that you get between xk and the xk prime, the thing that it's been mutated to. And it's always got two terms, something plus something. Okay. And then once you have the new seed, there's another procedure that says with the new seed, there's a new mutation matrix, and then it's like this, I guess it's like a tree of some sort, right? An n regular tree. So you start out with the new seed, you get m mutations, and from each of those you get another m mutations. Okay? And by definition, this is going to be some kind of algebra based on, okay, so generated by x1 through, this should be xm, and there's some relations going on here, right? But in any case, this is a subalgebra of a field. A field has no zero divisors, and so this cluster algebra has no zero divisors by definition. Okay? So an example of this, so let me just do an example just so that it's clear. So suppose I pick an initial seed x1, x2, x3, and I have some initial skew symmetric matrix that's going to be my exchange matrix. This exchange matrix will tell me how to mutate. Okay? So suppose I mutate along the x2, right? So I take x2 and I mutate. So everyone else but x2 stays the same. So x1 and x1 prime are the same, x3 and x3 prime are the same. x2 times x2 prime is going to be a sum of two terms. And what you do is you look up and down, I can't remember if it's up and down or left and right along this matrix. And if you have a positive coordinate, you put that up to this upstairs. So this is x1 squared. And then if it has a negative coordinate, you put it as in the second term is x3 squared. If there were more positive terms, they would all get lumped up with one of the ones with all the positives coordinates, and then the other one with all the negative entries. But it will always have something plus something according to whether this is positive or negative, and the number there corresponds to the exponent. Okay? And so equivalently now, whoa, there's a typo there. So x1 prime is equal to x1, ignore that x. But x2 prime now is some kind of Laurent polynomial in the previous terms. Okay? And then there's some formula which is complicated to tell you how you get this new exchange matrix. Okay, and so then you can mutate from the new cluster. Okay, so an important example of this is a cluster algebra of a surface. And so suppose sigma is a surface with punctures, and you fix an ideal triangulation. So the idea is that the edges of this triangulation are going to be the cluster variables. Okay, so that's your initial seed. And every time you do a mutation, actually, it's the initial seed, and then I also need the exchange matrix. The exchange matrix is just the signed adjacency. How many times is xi on the left of the xj minus the number of times that the edge xi is on the right of xj. Okay, so this is, okay, and then if I do a diagonal exchange, right, I do a Pochner move, right, this should be the mutation, okay? And the idea is that if I do a mutation, then xi along xi, then xi times xi prime should be the product of xaxc minus xbxd, and immediately they should think, ding, 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 this is the Ptolemy relation that we saw for decorated Teichmuller space, right? And I guess this is actually older than that, right? It's due to Ptolemy. And so the idea is that we want to identify these cluster variables correspond with the lambda lengths of the edges, right? Because they both satisfy this Ptolemy relation. And the idea is really that this cluster algebra is the corresponding cluster algebra that comes from the decorated Teichmuller space due to Penner. Okay, great. And here I say we would like, there's a small problem, a small technical problem in doing this in the case of a punctured surface. And the small problem is that in the definition of a cluster algebra, you need to be able to mutate along every single cluster variable in a seed, right? So you should be able to flip every single edge, but in an ideal triangulation, sometimes it's possible you can't always flip every edge. So for example, in here, so I'm gonna replace that orange one. I can do a flip and replace it with this other orange one. But now if I want to flip the red one, then I'm stuck. I don't know where to go, right? So this means that not every edge is flippable. This means that it's not quite in cluster algebra, and so you need to fix this. And this fix was done by Fuhrman, Shapiro, and Thurston. And what they did is they just did the combinatorics and said, what extra data do I need to add to the edges to make everything flippable? And so what they did is that they added these things called a decoration, these tags at the ends of arcs. So every arc at the end can be tagged or plain, so notched or plain. And so there's this extra tagging, and there's some rules for the extra tagging. So, but with this extra tagging data, so if it's complicated, then you get that every tagged ideal triangulation is flippable, and so therefore you do get a cluster algebra if you look at the tagged triangulations. So if the underlying, there's some rules about, so this over here is if the underlying arcs are equal, so for example this red one and this blue one, then you must have a same tag on at least one end, so down on the bottom of the same. But if the underlying arcs are different, but they share a vertex, then they must have the same tag. So over here, they have the same tag. Both the blue and red share the same vertex. Here, they're different. Here, they're different. And so there's some kind of way this extra tagging rules make it so that everything is flippable. Okay? And so what Hanbaum and I showed is that there's an algebra monomorphism from the cluster algebra to the Skein algebra. And again, this to the experts, this isn't really surprising because they both come from the combinatorics of the edges, lambda lengths from the Penner's decorated Teichmuller space. But what we really liked about our proof is that there's an explicit map, and it says that if you have an arc with the tagging that goes from V to W and it has tagging, then to get to a Skein in the Skein algebra, what you do is you take V, which is one of the endpoints, and you put as a power the number of tags that end at V, times W times the number of tags that end at W. So those numbers are either 0 or 1. And then you multiply it by the Skein that you get, or the arc that you get without the tags. Right? So somehow it says those taggings detect the lengths of the vertices, right? Because the V's and the W's in the Skein algebra came from lambda lengths of vertices. In other words, the lambda lengths of those vertices were the lengths of the horospheres that I chose as decorations on those punctures. So somehow, what we thought was nice was that the cluster algebra version, the tagging was completely combinatorial, and now we have some kind of way of thinking about it in terms of hyperbolic geometry. In addition, the two algebras have the same field of fractions, and so it follows that the quantization of the Skein algebra is also a quantization of the cluster algebra. So in this work, we're using the cluster algebra, which has nice algebraic properties, to get nice algebraic properties of the Skein algebra. But so again, I shouldn't say too much about this, but you can also go in the other direction, that the Skein algebra has nice algebraic properties. For example, it's finitely generated. We know presentations of them for some small surfaces, and maybe you can port that back into the cluster algebra world. And so that's the second half of our paper, and I think I want to stop here and thank you for your attention.
Questions or comments? Yes.
Thank you for a nice talk. So what about the Azumaya property in the punctured case?
Oh, we don't know anything. So this is just this is the first step where you have that it's a deformation quantization to begin with. Mm-hmm. To get the Azumaya stuff, I think you need to understand the center. We don't know what the center is. We think it should be related to this. Obviously, the central elements in the Skein algebra should also be central, but are there others? We don't know. We don't know about the representations. It's just, yeah, this is just the tip of the iceberg.
Okay, thank you.
No, thank you.
Thanks. If you're looking at the punctured surface, and you've got the curves for the Skein algebra that avoid the punctures, do you also have the facility, you were talking about arcs from puncture to puncture, can you be thinking of tangles, effectively, in surface cross I with endpoints at the top
yes,
and
exactly.
At the bottom?
So that's this generalization allows you to take tangles from puncture to puncture, yeah. Whereas in the original one, that wasn't possible.
Yeah, so that fits in the model.
Yes, exactly. Exactly. Actually, I should also point out that there's, Muller also defined a generalization in the Skein algebra. So for us, the punctures were interior punctures, but you can also have marked points on boundaries. The surface can have boundary and you can have marked points on the boundary, and there's also a cluster algebra structure for that. The relations are slightly different, and I know Tong knows much more about that than I do. But that also is related to the decorated Teichmüller space.
You are considering this non-oriented Skein algebras. So I'm curious whether for the oriented case, it seems that nobody cares about what's the situation of this oriented Skein modules. Or?
Yeah, I think people care, and I think I'm going to point you to Peter Samuelson over there in the back. So yes, I think there's other work on oriented versions.
But do you expect that they have some similar properties in your?
Again, we think there is, but again, I'm going to point you to Peter Samuelson.
Any other questions or comments?
So yeah, I can talk with you a little bit more after.
Okay. I was pleased to see the Ptolemy relations showing up. So thanks.
Yes.
So the question is this a simple incarnation of trace formulas, or is there a deep geometric explanation?
Oh yeah, no. So coming up with those extra relations, mm-hmm. right? Besides the Ptolemy is clearly hyperbolic geometry, and then the other ones involving the lambda lengths of the punctures and the knots, that requires pages of hyperbolic geometry proofs, like many pages. So, and that's all in Kant's work.
Who do I have to ask? Sorry?
Who are you pointing to? In the green in the back.
Questions? Any more questions or comments?
Yeah, what's nice about the relations is that the Skein algebra relations for these the arcs really come from the hyperbolic geometry. Like the hyperbolic geometry is dictating that those must be the relations. And what's interesting, the algebra, that stuff that I do is just to say, yes, those are the only relations that you need.
So if there's no more questions, let's thank Ellen again for the introduction.
you.